Okay, so hello everyone. I am Jet, and today, or tonight rather, since it's like 12 a.m. here now, we will be discussing a little bit about functions. So before anything else, I would just like to give some special thanks to Dr. Renson A. Robles, our differential calculus professor. Uh, he's going through a lot right now, so I just hope na things will get better for him soon. I hope he won't lose his passion for teaching students like us to become successful engineers in the future. And I would also like to give some shout outs to my blockmates, the section of ME1103. All I can say is that you guys are crazy, but it's been fun. Even though it's just been roughly 2 weeks, we've got to know each other kind of on the surface level rather, and I hope that I can be with you guys through my engineering journey. So, ayan. So let's get straight to the point now. We will be discussing a little bit about functions. Just a little disclaimer, I am no professional. And here I am, a freshman student entering mechanical engineering. So it's just an application of the Feynman technique. So if you can learn something, then that's good. So yeah, functions. So aside from the definition that it is the set of ordered pairs x and y that appear in the Cartesian plane, it is the general foundation of algebra, calculus, and the such. So we will also discuss its properties such as the domain and the range, the asymptotes, the intercepts, as well as how to graph some functions. So let's get straight into our set of examples. Okay. So it already has some answers, but I will just run through some of the answers. So for our first example, number 1, we have y equals 4x plus 8. Now you might wonder how we will get its domain and the range, the asymptotes, the intercepts, as well as how we can graph it. So it's all here. So for the domain of the function is basically the x. The domain is all the possible values of x that will give you a defined answer. And since we can put 0 here, 4 times 0 is 0, 0 plus 8 is 8, it is defined. If we put 1 half, that will be 2, 2 plus 8 is 10. So even if you put in a negative number, like let's say negative 1000, 4 times negative 1000 is negative 4000 plus 8, that is negative 3992. So it is defined. So our domain is from negative infinity to positive infinity. If we want to write that in set builder notation, that would be this x such that x is an element of all real numbers. That would be this is the interval notation, and this is the set builder notation. And then our range, the range is all the permissible values of y. So basically the range is all the possible answers of y. So if we set it into 0, like we did earlier, if we set this into 0, that will be 8. And if we input any values of x in there, we would still approach negative infinity. We will still approach infinity from negative infinity. So our range is from negative infinity to positive infinity. So in set builder notation, that would be y such that y is an element of all real numbers. Okay. Now this is where it gets kind of tricky, since we have the question: do asymptotes exist in this function? We see y equals 4x plus 8 is a linear function, so no. So we will see why it doesn't have asymptotes. I will explain what asymptotes are in a bit. So yeah. And now intercepts. Intercepts are another important aspect of functions. So the x and the y-intercept are very important, since the x-intercept is basically where the line passes through the x-axis, and the y-intercept is where the line or the curve passes through to the y-axis. So to solve for the x-intercept, we just set y equals to 0, and then we solve for x, like in this example. We set y into 0, and then we solve for x. This is some simple algebra here. And then for the y-intercept, we just set x equals 0 and then solve for y. So we set the x function, the x to 0, and then we solve for y. And now we see our x-intercept is negative 2, and our y-intercept is 8. So we can go to the Cartesian plane and plot those 2 points. So it would be roughly here. This is where negative 2 is on the x-axis, since that is the x-intercept, and this is where our y-intercept is on 8, positive 8. So if you trace those 2 points, it forms a straight line, or if you want to look at it from that perspective, it is a slanted line. So it stretches from negative infinity to positive infinity, as shown in our domain. And an important note to notice is that when we have the slope-intercept form y equals mx plus b, the b is the y-intercept. So just important to note that. Okay. Number 2. Now we have an exponent. We have y equals x squared. Again, the domain is all the possible values of x that will give you a defined answer. So again, it is from negative infinity to positive infinity, same as the range. And now for our asymptotes, we will get into that a bit later, since this function doesn't have asymptotes, since it is a parabola. So we go to our intercepts, and we just solve for it. Set y equals to 0, solve for x, set x equals to 0, solve for y, and both are equal to 0, so it starts from the origin. And now we see that the behavior of the graph is a parabola. Therefore, the x squared is the parent function for parabolas. Alright? So, now, number 3. F of x is equal to x squared plus 4. So for the domain, again, all the admissible values of x that will give you a defined answer is part of the domain. So that is from negative infinity to positive infinity. And for the range, now you might be wondering why this is not the same as the domain now. Well, you see, when we set x into 0, we get 4. since 0 plus 4 is 4. So therefore our range at 0, when x is equal to 0, we get 4. So how about when we set that into like 1 squared plus 4 is equal to 5. So you see from this range, it is possible that our values will approach infinity, as we can see from the domain. So let's see from our intercepts. So for our x-intercept, there are no real solutions. That is because this function cannot equate into 0. You'll see later. For our y-intercept, we just set x equals 0 and then solve for y, and then get the answer. So we have parabola. Again, this is just a transformation of the parent function x squared. It moved 4 units up. So take note that there's no x-intercept as the curve did not touch the x-axis. See? That is why there's no x-intercept. That is why it had no real solutions. Okay? And you can see from the range, it's because it's only covering this part. That is the range of the function. It doesn't include all these other parts here. So you can base that from the range. Now, another transformation of a parabola. Now we have x squared minus 4. f of x is equal to x squared minus 4. Again, the domain is all the permissible values, all the admissible values rather, of x. And for the range this time, when x is equal to 0, we have negative 4. Henceforth, our range is from negative 4 to positive infinity. We'll see. Same with this function. It doesn't include all the other parts of the Cartesian plane. It is on 4. See? Now if we look at this from the x-intercept to the y-intercept, now this is kind of tricky since there's an exponent now. So when we set y equals 0 and then solve for x, we have to square this number so that we can cancel the exponent. Therefore, the square root of 4 is positive and negative 2. That is our x-intercept. You'll see much later why it is positive and negative. And for y-intercept, just typically set x into equals 0 and then solve for y. And now we have another parabola here. Now we can see that it passes through negative 2 and positive 2. Henceforth, that is why we have this answer for our intercepts. And for the range, again, negative 4. It doesn't include all the other parts of the function. So everything from negative 4 up to infinity is just enclosed within this parabola. Alright? Okay, let's move on. Okay. Now we have y equals x cubed plus 2. So just a little bit of advice. When you have a cubic function, the domain and the range will most likely be from negative infinity to positive infinity. It depends on the function, but that is mostly why, since if you if you cube a negative number, then it will stay as negative, and then if obviously if you square a positive number, it will stay as positive. So that's why it works. So for our intercepts, again, since it is a cubic expression, we have to get the cube root to cancel this cube. So our x-intercept is the negative cube root of 2, and for y-intercept, again, just set x to equals 0 and then solve for y. Now, basing from these intercepts and from this table of values, since we just want to see the behavior of the graph, even though Sir Ranson said that the table of values should not be used now and in college level. This is just to show some perspective on how we can see the behavior of graphs. So plotting 5 points is enough. So when x is negative 2, and this is negative 2, that would be negative 2, that will be negative 8 plus 2, negative 6, right? When x is negative 1, it will be 1, 0 will be 2, when it is 1, it will be 3, and so on. So when we plot these points, these are the points right here, and we trace them, you would have what you call a cubic curve. And that is a property, or that is how cubic functions would look like. Alright, moving on. Now we have a square root. We have y equals the square root of x plus 2. Now, this is where it gets tricky now. Since it is a square root function, the value of what is inside the square root cannot be negative, since you can't square a negative number. That's why the domain starts from negative 2, and it is inclusive. When it is inclusive, there are no values that can be bigger than negative 2 that would work out for this. Let's say negative 2.000001. The result would still be negative, and you can't square it. Like, let's say negative 3. Negative 3 plus 2 will be negative 1. The square root of negative 1 is a complex number, which is not a real number. So that is why our domain starts from negative 2 up to positive infinity. For our range, it goes from 0 to positive infinity. So when you set the reason why it is 0 is that square root cannot be negative. The square root cannot be negative. Okay, now solving for the intercepts. Again, this is just some simple algebra. Set y equals to 0 and some solve for x. As you can see, you add the square root, add a square here to cancel this out, and then just transpose this there. For y-intercept, it is the same. It is basically, it's the same but just inverted. X equals 0 and solve for y. See? And now just ignore the asymptotes for now. We'll get to that very soon. So as we can see from our table of values here, negative 2 to positive 2, the value of y increases. It increases with the value of x. Alright? So if we plot these points on the graph, we will have this kind of arrow. this kind of direction. So that is a square root function. Alright? Or what you would commonly call an exponential function, but it is kind of different from this. So yeah, moving on. Now we have another square root function, but this time it's much more complex. We'll see. So we have f of x is equal to the square root of x squared minus 36. So the domain, again, what's inside the square root cannot be negative. So the domain is from negative infinity to negative 6, because negative 6 squared is 36. 36 minus 36 is 0. The square root of 0 is 0. So that's why this is allowed. Union, positive 6. It is the same. 6 squared, 36 minus 36. You'll get 0. Okay? And if we set this to a larger number, like if what I mean is a lower number, my apologies, let's say 5 squared is 25 minus 36, that's negative 11. You can square that. So that is why the domain is this. For our range, again, it cannot be negative, so a square root cannot be negative, so we start at 0 up to positive infinity. Now, asymptotes. Okay, let's try to get to the intercepts first before we discuss the asymptotes. So computing for the x-intercept, again, set y equals to 0 and then solve for x. So again, just transposing some stuff here, simple algebra, factoring this function. So we have two x-intercepts, positive 6 and negative 6, and the y-intercept, it cannot be negative, since that will be negative 36, and you can't square a negative number. That's why it does not exist, and you can see it in the graph later. So alright, okay, now you will see here when we try to simplify this equation here, if we try to cancel the square root, then transpose the square here, and then we will divide both sides of the function by 36, we will have this. Now what does this look like? It looks like the equation for a hyperbola, or a squared over a minus b squared over b is equal to 1. That is a hyperbola, conic sections, where a squared is 36, a is 6, since we just square that, b squared is equal to 36, and b equals 6. Okay. Now let's see the graph here. Now, since we have our vertices right here, it's a part of hyperbolas. So we go from 6, positive 6 and negative 6. That is where we will start our graph, and then from the top, this is where we make our square, since the origin is at it is at the origin 0, 0. So the asymptotes will appear from the side of the square. So generally, what are asymptotes? So asymptotes are values that the curve will approach but never reach, if that makes sense. So let's say this curve can approach this asymptote, but it will never reach or pass through this asymptote. That is what asymptotes are. Then we have the foci right here. This is a common part of hyperbolas, and yeah, that is how complex some functions can work. So I hope that made sense. So let's move on for now. All right. Now we have f of x is equal to the square root of 25 minus x squared. Now, first, before we define the domain and the range, we can just simplify the equation first. Again, to remove the square root, just transpose square here. Okay, and then you will transfer the 25. No, we'll transfer x to the side, so you will have x plus y squared is equal to 25, or 5 squared. Okay. Now what does that look like? That looks like an equation for a circle. So looking at this, the domain and the range, again, it cannot be 0. No, it cannot be negative. Yeah, it cannot be negative, since you can't square negative numbers. Just sounding like a broken record by now. And for the range, it will be 0 to positive 5. Why doesn't it approach infinity? Look at this graph. It only approaches the areas within 5. You see? Where the radius is 5. So, this circle obviously has no asymptotes. And yeah, for the intercepts, you can just compute through that. So positive and negative 5 actually will give you x, since this is the x-intercepts, this is the y-intercept. And you can flip this part of the circle, you can cut parts into the circle, and then you will change the equation. So this equation right here is the upper portion of the circle, this part of the circle. Since y, it is going to y, which means going up, it's positive, so that's this part. When y is negative, it's going down. And now when we start from x is positive, it goes here, and this covers this part of the circle. And then when the x is negative, it goes from here, and then it covers this part of the circle. Right? If that made sense. Now, for our number 9, we will be basing the properties of the function from a graph. So, in calculus, or in algebra in general, we will have to deal with graphs most of the time. We are not given functions most of the time, since we have to enhance our critical thinking and our analytical skills. So let's say we have this line right here. It is a linear function, right? So first off, what we can do when we have this line is we can determine the x-intercept and the y-intercept. When for this kind of line, since it approaches the y-axis and the x-axis, So our x-intercept is 1, right? And our y-intercept is 2. So we just paste that from the function. And since we have those intercepts now, and we see that the behavior of the function, we can say that the domain is the set of all real numbers as well as the range. So actually that is y. Hold on. It's actually y is the set of all real numbers. Sorry for that. And again, to determine how the direction of the function will go, we can do the rise over run method. So we calculate how much it rises. That means to y, and how much it runs, which means it's going to the x-axis. See, run. So we have 2 over -1. So why is it -1? We simply go through here. It rises for every -1 it travels, it rises by 2. Or we could say that for every 2 it travels, it goes by -1. So divide that, we get 2. And now if we put everything there into the slope-intercept formula, slope-intercept form, which is y equals mx plus b, then we get y is equal to -2x. This is our m, this is our slope, plus 2, which is our y-intercept. See, so we got the data of the function, we constructed the function from the graph. So there will be more complex graphs that we will deal with, and this is the basic way on how we would get it. Again, I'm just no professional here, just imparting knowledge. You can just adhere to the module if you're confused. There are the lessons there that you can read. And let's move on now. We have a rational function. So when we say rational, it is a fraction. So we have y equals 3 over x plus 3. Now, the special thing here is that the denominator cannot be equal to 0. Why? Because you can't divide by 0. It will be undefined. So it cannot be -3, because -3 plus +3 is 0. So 3 over 0 will not give you a defined answer. That is why hence there's a union here. But everything else will give you an answer. And from a range, basing from this, we base it from the domain. So when x is equal to -3, it will be 0. So I think 0 is included in the range. It's a possible answer. However, if you divide something, you're gonna get 0. You get what I'm saying? That's why there's a union here to separate the zeros from -infinity to +infinity. Because you cannot divide something and get a 0, right? So y cannot be equal to 0. You see? Therefore, this on rational functions, we will deal with how we will deal with the horizontal and the vertical asymptotes. So let's go over here for now. to get the vertical asymptote, just get the function from below and solve for x. So transposing here, and we have x equals -3. That is our vertical asymptote. Hold on, my throat is a bit runny from all the talking. It's almost 1 a.m. Alright, let's continue. So since y cannot be 0, our horizontal asymptote, therefore our horizontal asymptote is 0. That is also since the degree of the denominator is bigger than the denominator, than the numerator rather. Since when n is greater than m, therefore the horizontal asymptote will be 0. Okay? Now we can try to graph it. Okay. The vertical asymptote is -3, so we set that, and our horizontal asymptote is 0. Take note that when the numerator is constant, then you will do the curve from quadrant 1 and quadrant 3. That is when there is no this is when there's only constants on your numerator, and when it has an x or such, you will graph it from this side, from quadrants 2 and 4. Okay, so as we can see, hold on. As we can see from here, when x from this side approaches positive infinity, since it will just continue, y gets closer and closer to 0. That is how asymptotes work. And let's try from this side, since it covers this side right here. Let's try from this side. As y approaches positive infinity, x will approach -3. You see what's going on here. Y will just rise up and up and up. However, the asymptote here will prevent x, will generally prevent it, but it will still approach positive infinity, while x will approach -3 but will never reach it. That is the concept of asymptotes. Same with this. As y approaches -infinity, x will approach -3. See, you can see what do you call that? How it reflects from the axis, from the x and y axis, and from this part, as x approaches -infinity, y approaches 0. Yeah, it's that simple. Alright, let's move on. Now this is the parent function, actually, of the rational function 1 over x. Now again, x cannot be equal to 0, since it will be undefined. So when this is how the domain works, as well as the range, since y cannot be 0. since it is a rational function. And actually, I think I made a mistake here. Let me just correct that. Okay. Since n, the degree of n, which is the denominator, is greater than m. If you're wondering what the degrees are, this is the degree of the powers, of the exponents. So the degree of this is 1, while the degree of this is 0. Same with this. The degree of x sub n and 3 sub n, this is 0, the degree of 0, and this is the degree of 1. That is why n is greater than m. When n is greater than m, based from the theorem, the horizontal asymptote will be equal to 0. Okay? And if we solve for x, we just set x equals to 0, literally. That is our vertical asymptote. That is why this is considered a transformation of the parent function 1 over x. Okay? Since it has the same behaviors as this. So when you have the horizontal and the vertical asymptote equal to 0, again, when the numerator is just a constant, you start at these quadrants, from here to here and here. Okay, so again, when x approaches positive infinity, y approaches 0. This is for this part. And when y approaches positive infinity, x approaches 0. And you can say the same about these parts. When y, let's just erase this. So when y is approaching negative infinity, x approaches 0. Same with this. X approaches negative infinity, y approaches 0. You can see how the asymptotes come into work. Okay. Some more problems here. All right. Now we have this function y is equals to 1 over x minus 4. So for the domain, x cannot be 4, since it will result in the denominator being 0. Dividing by 0 is, again, undefined. And for the range, y cannot be 0, since it is a rational function. So to get the vertical asymptote, just solve for this, solve for x. Set is the same as to how you would compute for the y-intercept. Yes, set y into 0 and solve for x, but just don't include the numerator, I guess. And since the degree of the denominator is greater than the numerator, therefore our horizontal asymptote will be y equals 0. You see, this is just another transformation of the parent function 1 over x. So you see, it is just positioned here, since the asymptote x minus 4 is located here. And again, you can see it for yourself on how we can deal with these functions right here. Alright. Okay. Now what if we invert it? We have y equals 1 over 4 minus x now as a function. So the domain and the range will stay the same. However, and you can still get the same asymptotes. However, the direction in which it will approach will be different. You can see. So if x plus or minus a will result in this kind of direction within the curve like this, when you have an a plus or minus x in your denominator, then your function will look like this. That is when your numerator is a constant, and if and only if your numerator is a constant, and I think, then it will look like this. It will be inverted. You see, this transformed into this. It switched places. It was right here earlier, and this which was supposed to be here, now it switched to that. You see, we just inverted the location of the values of the denominator, and you can see how it changes the function. Alright, moving on. Now have y is equal to 3 over x plus 6. Again, this is what I've said, cannot be 0. This whole thing right here cannot be equal to 0, since it will be undefined. Same as the range, all that good stuff. The degree of the denominator is greater than the degree of the numerator. Is that right? The degree of the denominator is greater than the numerator. Therefore, our horizontal asymptote is 0. Okay? And since it is a constant, you just graph that from quadrant 1 and quadrant 3. Okay? Alright. Now, for number 15, we have y equals 3x over x plus 2. Now, this is what I was talking about earlier. So again, the domain, this is the set builder notation. Don't get confused. So let me just fix this a bit. It's supposed to be like that. Okay. The domain is x such that x is an element of all real numbers, except x cannot be equal to -2, since that will give you a 0. And for the range, to compute for the range of this function, is we can do some little algebra. So from this part, we can cross multiply this function. So we set a 1 here, so we can isolate the 3x. So when we multiply y to x plus 2, we have this. And now we distribute y into these values. So we have xy plus 2y equals 3x. And now we will what do you call it? We will transpose this term 3x and 2y, so that there may be like terms of x in terms of x. You see? So yeah, so it will be xy minus 3x, which we just transposed, is equal to -2y. We also transpose that. And now when we go here, we just factor out x, xy minus 3x, which will be x times y minus 3 is equal to -2y. Divide both sides by y minus 3 to isolate this x, and then we will have our answer, which is -2y over y minus 3. Now we look at the denominator and base the range on that. So when it is 3, that means y cannot be equal to 3, since that will give you a 0. And it cannot be equal to 0, since that will be undefined. That is why a range is the set of all real numbers except that it's y such that y is an element of all real numbers except y cannot be equal to negative 2 to 3. Okay, so again, to solve for the vertical asymptote, just solve for this in terms of y. So we set y to 0 and then solve for x. And now the theorem suggests that when the degree of the denominator n, a sub n, I think b sub n, is equal to the degree of the numerator a sub n, a sub m, then the horizontal asymptote will be a over b. And a is 3, and then b is 1. So 3 over 1 is 3. That is our horizontal asymptote. And this is our vertical asymptote right here. Now this is what I was talking about earlier. So as we can see, like from this function, hold on. So as we can see from this function right here, it started from quadrant 1 up to quadrant 3. Since it is a constant, now we have an x. That is why we will start from this direction, the same as this one. We start from quadrant 2 and quadrant 4. 4. Yes. That is because we have a value of x in the numerator now. As we can see, again, as x approaches positive infinity, y approaches 3, and the same stuff goes on. Okay, so let's move on. It's already past 1 a.m. I have a class at 11 a.m. Okay. So okay, now we have another transformation of the function 1 over x. We've been doing a lot of rational functions. So it's y equals 4x plus 2 over x plus 1. Okay, so as we can see, the domain is the set of all real numbers, or just read it as x, such as x is an element of all real numbers except x cannot be equal to negative 1. Just pretend that there's an x here, except x can yeah, negative 1, since that will give you a 0, and we all know. Now to get the range, again, we'll just have to compute this in algebraic terms. So cross multiply and to isolate cross multiply so that you may be able to isolate the function. However, as we can see from this, I think I did it a little differently. I didn't cross multiply, instead I factored out the 4x plus 2 to something that can be cancelled. So I cancelled this x plus 1, so I was left with 2. So that hence 4 was the range, since y cannot be equal to 4. You see? Now again, solve for the vertical asymptote, just solve for the denominator in terms of y, and since n is the degree of n is equal to the degree of m, this is just a over b. Alright, over b. So 4/1, which is just 4. This is our horizontal asymptote. And we go here, and this is the behavior of the function. Okay. Now we move on. Are we in the right number? Yes, we're number 17. Now this is 1/x² minus 25. Now we have an exponent in our denominator, so we can factor that out. That's a horrible looking x. Okay. Since x² minus 25 is the same as x plus 5, quantity x plus 5 times quantity x minus 5. Now, hold on. Now for our domain, did I actually, I think I erased the solution for that. For our domain, we just know that we will just solve for these two values in terms of y. So equals 0. So it will just be negative x equals -5. It's just basically switching 5. This is the values that we can get from the domain and stuff. Okay. So the domain is from -infinity to -5 union from -5 to +5 union from positive rather 5 to +infinity. Okay. Since x cannot be equal to 5 or -5, you see, since it will give you 0. Okay. And for x-intercept, we will see why it does not exist, and we will see that on the graph. And for y-intercept, we just substitute 0 to x, so it will be -1/25. Since 0 minus 25 is 0, 1/-25 is equal to -1/25. Okay. Since we have two vertical asymptotes, you can see, this is where our domain kicks in. So you can see from -infinity to -5. This is where it is, because as let's say x, I think as y approaches -infinity, x approaches -5. See? And now as -5, it approaches -5 from this direction, but it will never reach it, same as in this direction. You see? And as, let's say, y approaches positive infinity, as y approaches positive infinity, x approaches 5. See? As simple as that. And as you're wondering why the x-intercept does not exist. The graph never touched the x-axis. That is why it does not have a x-intercept. Yeah. Now we interchange it, and we will get basically the inverse. You see? So it used to be up here. Now it is down there. It was down here. Now it's up there. It's down here. It's up here. Now it's down there. So again, it's just a transformation of the function. You see? So I hope it made sense. that when you interchange, let's say 1 1 over a minus x, this is a, then you will have an inverted function of the parent function, which is 1 over x, since 1 over x plus or minus a gives you what the original function must be. Since think of this in like actually 3D dimension. Let's think in 3 dimensions for a while. You see, when I fold this in a 3-dimensional world, they will all catch each other, like Professor Renson said. Same as this. When you fold these in a 3D world, they will catch each other. See how they are interconnected, although the asymptote separates them. See? And I think this is our last one. It is g of x equal to the square root of x squared plus 3x minus 28. Now, the domain. When it approaches negative infinity to negative 7, because even if you square a negative number, it will be positive, since negative times negative is positive. So when this is negative 7 squared, it will be 49. When this is 7, negative 7, it will be negative 21. Negative 21 minus 28 is negative 49. 49 minus 49 is 0. So it will satisfy this equation as being equal to 0. However, when you go let's say lower than this, let's say 6, it will be 36 minus 18 minus 28. That will give you a negative number. That is why the square root cannot be a negative number, as I have said many times. Union 4 squared 8, here's 4 12. Hold on, and this is 4 squared is 16. I was dumb. 16 plus 8, 16 plus 12 is 28, so it will be 0. Yeah, so when this is 4, it will be 16, so it will be 12, yes. So that is why the domain is from 4 to positive infinity, since when you have a value of 4 in this function, then it will be 0, satisfying the equation. In the range, again, the square root function cannot be negative, since that is why we're starting at 0 to positive infinity. Again, to find the intercepts, we have negative 7 and 4. I see, based from the domain. And from here, it approaches negative infinity, as we can see here. And from this part of the function, it is from 4 to positive infinity. See? It's right there. And I guess that's the last example I have for functions. So I guess that helps. I hope that helped you in dealing with functions in calculus, although there's actually no calculus yet here. This is just pure math, pure algebra and stuff. So uh, that sums up the video in its entirety. So I hope you have learned something. It's 1:18 a.m. here. So yeah, I guess thank you for giving the time to watch. If you watch the whole video, then I thank you very much. And that's it. I have to go sleep now since I have a class in around 10 hours. So yeah, that's it. Thank you guys, and bye bye.